Hello, Vacho, and welcome. Today, we are starting a very important chapter, atoms. Now, I know it can seem a little difficult, but trust me, we're going to break it down so simply you'll be all set to score full marks in your exams. So, let's begin.
Okay, let's get right into it. To get our minds warmed up, I want to start with a really simple question about something I'm sure all of you have seen.
You've noticed this, right? A neon sign always has that special reddish-orange glow. It's never green, it's never blue. Why is that? Just keep this little question in the back of your mind, because the answer is tied to a much bigger mystery.
Now look at this. This is actually quite shocking. Forgetting the neon signs for a moment, according to all the old physics, the physics of Newton, every single atom in the universe, the atom in your hand, in the chair you're sitting on, all of it should have collapsed in less than a second. But, obviously, they don't. We're here. The world is here. So what was so wrong with the old physics?
Well, to figure that out, scientists first had to guess what an atom even looked like from the inside. They knew it had parts, but how were they all arranged? What was the setup?
So by the late 1890s, a few things were very clear. We knew about these tiny negative particles called electrons, and we also knew that an atom overall is neutral. So it's just simple logic, right? There must be some positive charge inside to balance out all that negative charge from the electrons. The big question was, where was it?
And the first person to give a proper guess, a proper model, was J.J. Thomson. He came up with a simple idea, based on a sweet dish. For us here in India, a much better way to imagine it is like a watermelon. Or maybe even a bundi laddu, na?
Now this, bachon, this is the exact line from your NCERT textbook. For your exams, this is the definition you must write down. It's very simple. Just imagine the entire red part of the watermelon is a big ball of positive charge. And the black seeds that are stuck inside, those are the tiny negative electrons. A very simple picture, but it was a great first step.
But as you can probably guess, this watermelon model, it was wrong. It just couldn't explain why atoms were so stable. The real answer needed a completely new, a revolutionary idea that changed physics forever.
You see, even when we discovered that there's a nucleus at the center, the problem didn't go away. Think about it. A negative electron circling a positive nucleus. It should be constantly losing energy, right? Like a satellite running out of fuel. It should just spiral down and crash into the center. This was the biggest failure of classical physics. It was predicting a universe that would destroy itself.
And the solution? It came from the brilliant physicist Niels Bohr. He said something radical. He said the old rules are simply wrong at the atomic level. He said energy is quantized. This is the most important word today, quantized. It means energy only comes in fixed packets or chunks. It's not like a smooth flow of water from a tap. No, it's more like getting water in separate 1-liter bottles. You can have 1 bottle or 2 bottles, but nothing in between. This single idea was the start of a whole new science, quantum mechanics.
And this is the best way to understand it. Forget a smooth ramp. Just imagine a staircase. An electron can be on step number 1, or step number 2, or step number 3. But, and this is the key, it can never float in the empty space between the steps. It's just not allowed. And to go from a higher step to a lower one, it has to jump. And when it makes that jump, poof, it releases one fixed packet of energy in the form of light. And the size of that packet, which decides the color of the light, depends completely on the height of the step it jumped from.
And that, my friends, brings us right back to our first question. The neon atom has its own unique staircase, with its own fixed step heights. When its electrons get excited and then jump down, the energy packets they release have the exact energy of red light. They just cannot produce the energy packet for green light because they don't have a step of that particular height. See how it all connects? Simple, right?
Okay, fantastic. Now that you've got the main idea, let's switch gears and focus on what you absolutely need to know for your exams. And let's clear up some very common mistakes that students always make.
Please pay close attention here. I call these silent killers. Why? Because they seem like very small points. But making these mistakes tells the examiner that you haven't really understood the concept, you've just memorized it.
Okay, silent killer number 1. Thinking that electrons orbit the nucleus like planets orbiting the sun. No. A planet can change its orbit to any distance. An electron cannot. It is strictly stuck to its specific energy levels, just like you can only stand on the steps of the staircase, not in the air between them. So please, the planet model is the wrong picture to have in your head.
And silent killer number 2 is about temperature. So many students think that if you heat a gas more and more, the color of the light will change. That is incorrect. Remember, the color is decided by the height of those energy steps, and that is fixed for an element. Heating it more just makes the light brighter. That's it. It's because more electrons are making the same jump. The color of each individual light packet stays exactly the same.
So, for a quick revision, let's go over the main takeaways. 1. The old classical physics completely failed to explain why atoms are stable. 2. We know an atom has a tiny, positive nucleus with electrons around it. 3. And this is the magic word. Electron energy is quantized. It only exists in fixed levels. 4. Light of a specific color is given off when an electron jumps between these fixed levels. And finally, number 5. This whole idea of quantization is the reason atoms don't just collapse. It's the hero of our story.
And that leaves us with a really deep and fascinating question to think about. If the world at the tiniest level doesn't follow the nice, smooth rules we see all around us every day, if it's all about these weird jumps and steps, then what does that tell us about the fundamental rules of reality itself? This question is the doorway to the amazing world of quantum mechanics, a world we will explore later. Well done today, everyone.